I'm going to begin with a summary of the troubleshooting methodology. CompTIA recommends a 7-step troubleshooting methodology. Step 1 is to identify the problem. A mistake in identifying the problem can negate the rest of the steps. And remember, the problem is not the symptom. The problem what is causing the symptom to occur. Step 2, establish a theory of probable cause. Step 3, test the theory of probable cause. Once you have tested the theory of probable cause, move on to step 4, establish a plan of action to resolve the problem. Step 5 is implement the solution or escalate as necessary. Step 6 is to verify full system functionality. And your last step, step 7, is to document findings, actions, and outcomes. And there we have a brief review of the 7-step troubleshooting methodology. With that, let's move on to common copper wire problems. First up is electromagnetic interference, or EMI, and radio frequency interference, or RFI. Because copper wire transmissions are electrical in nature, their electrical signals can degrade by sources of either EMI or RFI. Sources of interference may corrupt the network signal, leading to a loss of communication or poor communication between end nodes. There are several possible sources of EMI and RFI. These include other electrical wires. Network cables should be kept separate from normal electrical runs, and if possible, network cabling should always cross electrical wires at a 90-degree angle. Never run network cables right alongside the normal electrical run, as the probability of interference will greatly increase. EMI and RFI can also be caused by other electrical components. Manufacturing environments often have a lot of EMI and RFI present. Another major source of interference is fluorescent lights. Interference problems can often be identified by when they occur. For instance, does the problem only happen when somebody turns on all the lights? The solution may be to move from UTP to SDP or to reroute the network cables to avoid the source of the EMI or RFI. All copper wire networks have distance limitations. And by that, all network transmission media experience attenuation, which is a loss of signal strength over distance. This can lead to poor communication or loss of communication between end nodes. A decibel logarithmic scale is used to measure the amount of acceptable and unacceptable attenuation. As network transmission speeds increase, the attenuation also increases as a ratio of signal to signal loss. Possible attenuation issues can be identified when a cable cannot handle the higher transmission speeds for which it is rated. A cable certifier or TDR will usually identify this problem. Possible solutions are to install a network switch to boost the signal strength or to reroute the network run to create a shorter run of cable. Then there's crosstalk. Even with the steps taken to reduce it, all cables experience crosstalk between the pairs, which can lead to intermittent or constant transmission issues. More crosstalk is present at the near end, where the transmissions originate, than at the far end, where the transmissions are received. As network transmission speeds increase, the opportunity for crosstalk increases. A good cable certifier or TDR will identify the problem. Possible solutions include replacing the network run with cable rated for a higher transmission speed, replacing the cables with one that has better shielding, or reducing the transmission rate of the network. Bad connectors are also a common problem on copper wire networks. Once a good cable is in use, the end connector may still become broken, especially after repeated use, leading to a loss in connectivity. In particular, this can happen on RJ45s. The locking tab can be easily broken, leading to a loose connection or creating an open connection. A cable tester may identify this problem as an open connection but a thorough inspection of the cable ends can help to identify the problem. The solution is to replace the bad connector with a good one with your crimper. Then there are bad cables. Cables can go bad, especially if they are in places susceptible to damage, leading to loss in connectivity or poor network communication. A cable tester can be used to identify the problem as either an open connection or a short. An open connection indicates a broken wire. A short indicates an electrical signal traveling down an unintended path, as in down the wrong wire. The solution is to replace the bad network cable. I'm going to begin with what constitutes a bad cable. Network cables can go bad or be bad without any visible indication. Additionally, a cable may be inappropriate for a particular application. Anything that makes a cable fall outside of specifications will make it a bad cable. How long is the cable? Is the cable over its maximum run length? Is the cable rated for the amount of data being run over the wire? All of these plus more can constitute a bad cable. By using the proper tools and methodology, a bad cable can be identified and any problems associated with the bad cable can be rectified. Let's talk about copper wire termination standards. They are currently established by the TIA-EIA, that is the Telecommunications Industry Association Electronic Industry Alliance. They have established a set of termination standards for twisted pair copper wire. The standards ensure that network transmission is consistent across networks. The standards involve how the pairs of wires are ordered when placed in the termination device, which is usually either an RJ45 or a punchdown block. The current standards are the T568B and the T568A standard. The pinout for the T568B standard is white orange orange, white green blue, white blue green, white brown brown. On the other hand, the pinout standard for the T568A standard is white green green, white orange blue, white blue orange, white brown brown. Not following the standards may lead to network problems. Cable testers and certifiers can be used to determine if a twisted pair copper wire network cable meets the standards. We're going to begin with twisted pair termination standards. A straight-through cable is used to connect different types of devices, e.g. a computer to a switch or a switch to a router. Both ends of the cables are terminated to the same standard. Alternatively, there's a crossover cable. A crossover cable is used to connect similar types of devices, as in a computer to a computer or a switch to a switch. One end will be terminated to the T568A standard and the other end will be terminated to the T568B standard. A problem can arise when you have mismatched cabling standards. Using the wrong type of cable, as in using a straight-through cable when a crossover cable is specified, can lead to network problems. Many IT devices use a process called auto MDI, MDI-X, in which they can auto-sense the type of device on the other end of the cable and electronically change their send-receive setup to match the cable used. But reliance on this may contribute to the problem. Cable testers can be used to help identify the problem in a mismatched cable standard. When creating your own cables, you may end up with split pairs. The problem occurs during the termination process. At least two pairs of wires that should be grouped together in the termination device get separated. The problem may not be identified with the most basic of cable testers. They will still test as having continuity from end to end. If the split pairs are due to a misunderstanding of the termination standards, it may still test as a straight-through or crossover cable. This often leads to a crosstalk issue. A good cable certifier will always identify the problem. Then there's the TX-RX reverse, or the transmit-receive reverse problem. A PC-type device always uses pins 1 and 2 as one pair of wires to transmit a signal and pins 3 and 6, another pair of wires, to receive a signal. The receiving device must be configured to either receive on pins 1 and 2 and transmit on pins 3 and 6, or the proper cable must be used, like a crossover cable. If not, the link will not be created. That is a TX-RX reverse. If the link fails to be created, check the pinout on the cables to ensure that a TX-RX reverse has not occurred. Now that